Take a breath and picture a simple scene: your laptop, a web browser, an email client, and a database somewhere in the cloud. Everything's humming along. You click a button, the interface updates, and you call it a day. Now imagine drawing an invisible line through that scene. On one side of the line is your browser running on your laptop, code you wrote, data you own, a session with your identity. On the other side is a remote database you don't control directly, hardware in a data center, separated by networks, routers, and authentication protocols. That invisible line, the place where your mental assumptions about safety and control change, is what we call a trust boundary. At first, that sounds almost disappointingly ordinary, but the point of this video is to show you how much power and how much fragility is packed into that simple concept. A trust boundary is the place where assumptions change. It's where promises you make about data, identity, and privilege stop being true unless you explicitly enforce them. And understanding where those lines are and why you drew them in the first place is the single best way to stop small mistakes from turning into catastrophic failures. So let's start with a concrete definition. A trust boundary is any point where the context of trust changes in a system. Context of trust means the set of guarantees you make about inputs, identities, or actions. On one side, you might assume these inputs are sanitized. This process only runs trusted code, or this user has admin rights. Across the line, those guarantees might not hold. That change in guarantees is the boundary. Think about it like a country border. When you are inside a country, different laws, different privileges, different services apply. When you cross the border, passports are checked, luggage may be inspected, and different licenses apply. If you treated a foreign driver's license as equivalent to a local one without checking, you would be making a risky assumption. Systems are the same. If your code blindly trusts an external input the same way it trusts an internal configuration file, you've just treated a foreign passport as a local ID, and that's dangerous. Now let's examine where these borders appear. They're everywhere, and they're often invisible. The HTTP endpoint that accepts user input is a boundary between the internet and your application. The API call between two microservices is a boundary between two trust zones. The system call that hands control from user code into kernel space is a boundary between unprivileged and privileged contexts. Even different teams inside an organization create trust boundaries when they hand off responsibility for a service. The backups team maintains these credentials. Don't touch them. Wherever responsibility, privileges, or assumptions shift, you've got a boundary. Why do we draw these boundaries at all? The answer is the same reason societies have borders: to manage risk and make complex systems tractable. Boundaries let you compartmentalize. If something goes wrong in one area, the boundary limits the blast radius. That's the principle of least privilege in action. Give each component only the authority it needs, and put a boundary where higher privilege begins. Imagine your data center as a ship with many compartments. If one compartment floods, watertight doors slow the spread so the whole ship doesn't sink. Trust boundaries act like those doors. When you design systems with clear boundaries and strict controls at each door, a breach in one module won't immediately let an attacker waltz through to the engine room and sink the ship. But notice the nuance: boundaries only help if they're enforced. A door with no lock is decoration. So much of security engineering is simply deciding where to put the doors and what locks to use. Should Service A be allowed to query Service B's entire database, or should it be restricted to a narrow read-only view? Should internal network traffic be implicitly trusted, or should each service authenticate and authorize every request? These design choices are why boundaries exist, to turn vague trust into enforceable contracts. Contracts. That's a useful mental image. On one side of a boundary, you publish an interface, an API, an authentication method, a file format, and you promise certain things about what you do and do not accept. On the other side, callers must meet that contract to be allowed across. That contract is where validation, authentication, and authorization live. Drawing a boundary without a clear contract is like agreeing to accept deliveries from anywhere and then being surprised when someone shows up with a truck full of explosives. This leads to an important cognitive step: recognizing assumptions. Every time you draw a boundary, you also make an assumption. We assume only admins can reach this endpoint. We assume internal network traffic is controlled. We assume this service only receives well-formed JSON. Many of these assumptions are implicit and unexamined. They become the weak points attackers look for. Let's walk through a small example. You have a web application that accepts uploaded images and stores them in a shared file system. The web server process runs as a regular user and puts files into a directory. Separately, a background job runs with higher privileges to process those images and write to an archival store. Where are the boundaries? There's the HTTP boundary between the internet and your web server. There's the Vorsystem boundary between untrusted uploads and the code that processes them. There's the privilege boundary between the web server and the archival job. If you assume that uploaded files are always safe and let the background job process them without validation, you've trusted across the boundary without enforcing the contract. An attacker might upload a specially crafted file that, when processed by the privileged job, executes code or escalates privileges. That small oversight at the boundary becomes a powerful attack vector. We can classify why boundaries help into a few practical principles. First, isolation reduces blast radius. If components are isolated and only expose minimal interfaces, an attacker needs many successful crossings to move from a peripheral compromise to a core breach. Second, least privilege reduces available exploits. If a service only has read access to what it needs, even a successful crossing won't let the attacker perform destructive actions. Third, explicit contracts make validation simple. When you precisely define what is allowed at the boundary, message formats, authentication, rate limits, it's far easier to instrument checks and detect anomalies. Fourth, defense in depth slows an attacker. Multiple boundaries in series, network segmentation, strong auth, per call authorization, logging, mean an attacker must bypass many independent controls, increasing the chance of detection. But there's equally important negative space, where boundaries fail. Boundaries fail in two common ways. One is implicit trust, assuming something is safe because it came from the inside. The other is drift. Over time, temporary exceptions accumulate until the boundary is porous. Maybe an engineer lets a debug endpoint remain open just for testing. Maybe a service account granted broad privileges for an emergency is never revoked. Each little exception chips away at the boundary until it's no longer a meaningful barrier. This is why discipline matters. When you design a system, don't just draw the boundary, write down the contract and automate the enforcement. Use IAC to prevent ad hoc changes, require short-lived credentials instead of static keys, and bake monitoring into every boundary so you can see when crossings happen that don't match the contract. One more subtle concept: partial trust. Not everything is either fully trusted or fully untrusted. Sometimes you need to accept a piece of data, but treat it with limited rights. For example, you might accept a user-uploaded document and render a thumbnail in a sandbox, never allowing it to be processed by privileged code. That pattern, dealing with partially trusted inputs, is a core tool for handling hostile worlds without assuming absolute safety. To bring this together, think of a well-engineered system as an archipelago rather than a single continent. Each island is a module with its own controls. Bridges connect islands, toll booths check travelers. A novice design ignores the bridges and expects everyone to behave. A mature design deliberately places toll booths, limits who can cross, and monitors the flows for suspicious traffic. So when you next look at your architecture diagram, don't just stare at boxes and arrows. Draw the trust boundaries explicitly. Ask, for each boundary, what contract do we expect? What privileges cross here? What assumptions are we making? How would an attacker try to cross? And what would we see if they did? If you do that, two things happen. First, your design becomes more defensible. You can point to a specific door and say, this is where we check authentication. This is where we validate input. This is where we drop privileges. Second, you gain clarity about trade-offs. Every added boundary increases complexity and latency. Every missing boundary increases risk. Security is about balancing those trade-offs in a way that makes sense for your assets and threat model. Thanks for watching.